So it's my pleasure to introduce Andrew McLeod, our second speaker of this session, who's from the Niels Bohr Institute. And the title of his talk is something that he couldn't get through physical review letters, but we're pretty lax here. It's a bounded bestiary of Calabi-Yau geometries in Feynman integrals. Andrew, please go ahead.
Thanks, Lance. You guys can hear me?
Yep.
Yeah, great. And thank you also to the organizers for putting on a great conference despite the circumstances. So as Lance said, I'll be talking about a bounded bestiary of Calabi-Yau geometries and Feynman integrals. And this is work published with my collaborators at the Niels Bohr Institute, Jacob Bergeli, Christian Bergu, Matthias Volk, Matt von Hippel, and Matthias Wilhelm. And it'll also be related to the material that Christian will talk about in the next talk slot. Oh. So just to briefly outline what I want to talk about today, I'm going to first review how geometric manifolds naturally appear in Feynman integrals and point to the need for more general classes of functions and polylogarithms. I'll then consider whether or not these manifolds can be arbitrarily complicated or if we can bound them. And of course, the answer will be yes. And having discussed that bound, I'll point to a few infinite classes of integrals that actually saturate this bound at all loop orders and give rise to the Calabi-Yau manifolds of the title. And finally, I'll try and further characterize the actual manifolds that we see appearing in quantum field theory. So to motivate broadly the question I want to talk about in this, this talk, let me just review quickly the modern pipeline for how we calculate quantities such as scattering amplitude using Feynman integrals. And that is to generally start with some kind of integrand level techniques such as generalized unitarity to identify a hopefully small set of integrals that are sufficient to compute the quantity we're interested in. We usually impose some kind of integration by parts identities to further reduce this number of integrals. But in the end of the day, we're left with some basis of master integrals that we want to evaluate in some way, shape, or form. Often we use techniques such as direct integration, differential equations, or bootstrap methods. But all of these techniques are fairly tied to our understanding of the types of special functions that these integrals evaluate to. And so that broadly is a question I want to address, which actually Claude brought up as a good question in his some of the introductory slides. And that is, what class of functions do Feynman integrals evaluate to? Now, it's certainly possible to investigate this question in a variety of contexts, such as different space-time dimensions, different theories with different matter content, etc. I'll mostly be focusing in this talk on finite integrals in integer dimensions. And I'm going to begin by just pointing out that at low loop orders, we can probe this question rather directly because we only have a couple of integrals to carry out. Because we all know that Feynman integrals start their lives as integrals of irrational functions of kinematics and loop momenta, or of Feynman parameters if you prefer. We also know that rational functions integrate to rational functions again, except in the presence of simple poles. And so what we can do is we can think, we can be boneheaded about it and we can just start integrating. And we'll hit some simple poles and generate some logarithms, and then we can keep going, and we very naturally encounter the space of so-called multiple polylogarithms, which were seen many times in the talks at this conference. So these are iterated integrals over rational functions on the punctured Riemann sphere, where this means we're talking about nested integrals, where the contour in each case you can imagine is something like this green line on the Riemann sphere, which you can just think of as the complex plane, which I've compactified by adding a point at infinity. And in addition, this Riemann sphere has some structure in the form of punctures, which is where my rational functions have simple poles. And in the context I'm talking about now, the location of these punctures will be determined by kinematics after the first three, which I can put at 0, 1, and infinity is generally where we put them using Mobius transformations. And of course, since these functions are generalizations of logarithms, they are in general very complicated multi-value transcendental functions. But luckily, there exists some well-developed technologies for imposing identities on these types of functions for their analytic continuation, which corresponds to deforming these contours around the simple poles, and for things like numerical evaluation. And I should mention that one of the key components of this technology is the coaction on polylogarithms from Gottschalk and Brown that Claude and Ruth talked about earlier. So another reason why this is an important class of functions for Feynman integrals is that it does seem like it's sufficient for one loop integrals in integer dimensions. However, as Claude pointed out, and as those of you who have been amplitudes for the last couple of years know, beyond one loop, this is certainly not the case. So it's easy to see how we break out of the space of functions in the following example. We can imagine we're integrating over a rational function that takes this form, where we have a quadratic equation in the denominator. And we can integrate this logarithmically by partial fractioning out and isolating the simple poles that appear in this expression, but only at the cost of including or introducing a square root of the discriminant in the prefactor. And so if we have further integrations to carry out, and if this discriminant f squared minus g depends on these remaining integration variables, it may be that we cannot carry out any further polylogarithmic integrations. So in very simple cases, we might be able to, like if we have repeated roots in these polynomials, we can pull them out, or if they're low degree, we can rationalize them potentially. But in cases where even only a single integration variable alpha remains and appears in a third or higher order polynomial, we can get things like elliptic curves appearing in the denominator in this way. And these can be described by introducing an auxiliary parameter y, which I've equated at the bottom here to some generic quartic polynomial where R1 through R4 are just some roots, which are going to be given by rational functions of the kinematics. And so this first obstruction to thinking in terms of multiple polylogarithms naturally gives rise to a generalized space of elliptic polylogarithms, which are now iterated integrals over rational functions of both alpha and y, where again, y is just this auxiliary parameter which satisfies this relation. And these types of integrals can also be formulated as integrals or iterated integrals on the moduli space of genus 1 Riemann surfaces, again with punctures like we had in the genus 0 case. Luckily, this space has nice properties like containing the space of multiple polylogarithms. And a lot of the technology that was useful in the polylog case actually can be generalized to help us in this case. And a lot of work has gone into this over the last couple of years. I've showed many of the names involved at the bottom. And actually, there's a great review, a better, more comprehensive review of what's been done in Claude's talk from Amplitude a couple of years ago. And I want to emphasize that in this case, just like in the polylog case, the geometry is again controlled by the kinematics and the functions we'll be looking at. So in addition to the locations of these punctures at sigma 2 and sigma 3, now we also have it controlling the shape of the torus in the sense that the relative length of the A and B cycles will be determined by kinematics. So of course, this is kind of the simplest thing that can appear beyond multiple polylogarithms. So in general, a larger number of integration variables can appear in these square roots, and here be dragons, or at least beasts of some kind. So in such cases, we get integrals over denominators that encode higher dimensional manifolds, and we can treat these or describe these in the same way as before by introducing an auxiliary parameter y again, and equating that to the polynomial inside the square root. And just like before, you can think of the remaining integration variables alpha I as being coordinates on this manifold, and then the kinematics in the form of, for instance, Mandelstam invariants and internal masses as controlling the shape of this manifold. So it's natural to then ask if these manifolds that appear can be arbitrarily complicated. And the answer turns out to be no. Turns out we can bound the so-called rigidity or dimension of these manifolds that appear. So to do so, let me make use of the semantic form of Feynman integrals, which is basically the Feynman parameter form. So I'll be looking at integrals that have E internal edges, L loops in D space-time dimensions. And my notation here is such that the integration measure is a projective integration measure. So there's actually an integral over all E of the Feynman parameters associated with internal edges, but one of them can always be done trivially with a delta function. So this form of these integrals is given in terms of a U and F polynomial, which can be given a graph theoretic definition in terms of spanning K forests. So let me give an example of how that works. So if we look first at the U polynomial, we have a sum over spanning one forest, which really just means a sum over all trees that span all the vertices in this diagram. And then we have a product in that term of the sum, we have a product over the Feynman variables that, or Feynman parameters that don't appear in this tree or are associated with the propagators that don't appear in this tree. And it's easy to see that that will give rise to a homogeneous polynomial of degree L because we need to cut open all L loops. So we basically delete L propagators from our original graph. And similarly, the F polynomial you can think of as a sum over spanning two forests, meaning we just have two trees that span all the vertices in our graph. And here we also have kinematics decorating these polynomials. So S sub T1 indicates the Mandelstam variable that's associated with the energy flowing into either of these two trees in the example at the bottom. And then here we also have additional contributions when the internal masses of the integrals we're looking at are non-zero. So I'll be making use of two simplifications that occur in certain cases. The first is that for certain integrals that satisfy this, one of these two relations between their number of edges, loops, and space-time dimensions, one of the semantic polynomials will drop out. And moreover, when all the internal edges of our graphs are 0, then both the U and F polynomials are linear in every one of the Feynman parameters. So just to get a little more specific, let me focus on massless integrals in 4 dimensions that have 2L plus 2 propagators. So these integrals take this form here where the U polynomial has dropped out. And due to the fact that these integrals are entirely massless, the F polynomials are linear in every Feynman parameter. And this means we can just directly integrate twice. So first we integrate with respect to alpha j, and then we integrate with respect to alpha k by just pulling off the coefficients of these Feynman parameters. And this gives rise to now an integral over a logarithm. And notice that in the denominator, we've not yet introduced an algebraic root of any kind. This is still just a polynomial. And since the original F polynomial was linear in every Feynman parameter, these factors at the bottom are still linear in every Feynman parameter. And moreover, if you follow the degree of the polynomial all the way through, you'll see that this denominator has degree 2L. So since all 4 of these factors in the green bubble here are linear in every remaining Feynman parameter, that means the denominator is just a quadratic equation in any given Feynman parameter. And so we can always do at least one more logarithmic integration like the example I showed a few slides ago. So doing that will give rise to an integral that just depends on 2L minus 2 more integrals. And that automatically bounds the rigidity or dimension of the manifold that can appear in these Feynman integrals to be less than or equal to 2L minus 2. So we can work through a similar argument in 2 space-time dimensions for graphs that have L plus 1 edges, where this is again the condition that makes the U polynomial drop out. But now we're going to require that all the propagators are massive, which makes the F polynomial automatically quadratic initially. And one can then show that the rigidity of these integrals is less than or equal to L minus 1. So when all possible integration orders lead to a square root in the denominator that is cubic or worse in all remaining integration variables and doesn't have repeated roots, for instance, we cannot do any further polylogarithmic integrations and we saturate these bounds. So when I say different integration orders, I just mean different choices for which Feynman parameter I'm integrating out at any step. So in fact, we can say more. So in the d equals 4 bound, we can continue to follow the degree of the homogeneous polynomial through. And we will find that the polynomial appearing in the square root will have degree 4L minus 2, in this case where we saturate the bound. And there'll be 2L minus 1 remaining Feynman parameters inside it. So that means it describes a surface and weighted projective space, where weighted projective space is just a complex vector space where we've deleted the origin and then modeled out by some rescaling relation, but we've weighted the rescalings by the weight of each variable. So I will be weighting all of the remaining Feynman parameters just by weight 1, whereas the auxiliary parameter y will be weighted by 2L minus 1. So the key here is that it turns out that it's a sufficient condition for the or if the sum of the weights equal to the degree of the polynomial, this is a sufficient condition for this manifold to describe a Calabi-Yau. And so these are, of course, the Calabi-Yaus of the title. And anytime we find a Feynman integral that saturates these bounds, they're automatically guaranteed to be Calabi-Yau. So this is all very nice and abstract, but of course I should convince you that there are actually integrals that satisfy this bound, and we've, it turns out, found a few infinite classes of them, a veritable bestiary of them. So all three of these classes we pointed to when we published this. And so the tardigrades at even loop orders and the paramecia and amoebas at odd loop orders all give rise to integrals of dilogarithms over Calabi-Yau 2L minus 2 folds, meaning the Calabi-Yau manifolds are 2L minus 2 dimensional. And it's worth pointing out that already at 2 loops, this tardigrade class gives rise to a K3 manifold. And even though I don't remember Enrico emphasizing it, the integrands that appeared in the basis of MHV 2-loop integrands he talked about actually have support on this 6 cut. So it's very relevant to n equals 4. Although in that case, in the MHV case, we know this K3 contribution has to cancel out, and indeed you can see that happens. But this has n squared MHV support in n equals 4. Moreover, if you just look at the vertices, you can see that this is a contribution to massless phi to the 4th theory. So there's no avoiding this integral. So the well-studied all-mass L-loop banana or sunrise integrals also saturate the d equals 2 bound. This was, of course, not pointed out by us because these integrals have been studied much longer. But these integrals all give rise to integrals of logarithms over Calabi-Yau L minus 1 folds. So having gone through that argument, I should make 2 provisos. The first is that we haven't actually ruled out the existence of potentially intricate changes of variables that might rationalize these roots, although we don't know of any examples where this can be done. And probably more importantly, the manifolds that appear in this procedure are in general, very singular. And it's easy to see this is the case because all the infinite classes that I pointed to have a fixed number of external legs. And so in general, the number of independent kinematic degrees of freedom will be much smaller than the number of complex structure moduli determining the shape of these Calabi-Yau manifolds. And as such, they might not have all the nice properties usually associated with these types of manifolds. But in some sense, it's not clear that we care because these manifolds are quite a bit more special than generic Calabi-Yaus. For one, there are many fewer Feynman integrals needed to express scattering amplitudes at low loop orders than there are Calabi-Yau manifolds. And moreover, we've shown that these examples, and actually some more examples, can be realized as hypersurfaces and weighted projective spaces of this type. So in addition to the non-planar integrals that I showed a few slides ago, we've also been able to show that this 3-loop train track gives rise to a Calabi-Yau that can be embedded in 3-1-1-1 weighted projective space. And similarly, this 3-loop wheel can be embedded in 4-1-1-1-1 weighted projective space. So since many of the examples we know about, almost all the examples we know about, can be embedded in weighted projective space in this way, it's natural to ask whether we can further characterize these manifolds. And so the types of things we can say about them is, for instance, we can calculate their number of complex structure moduli. So this is just the number of independent coefficients entering these defining polynomials. The y-squared polynomial. We can compute things like their Hodge diamonds, which gives the dimensions of their Dalbo cohomology groups. So for instance, for the k equals 5 case, which corresponds to 3 loops in the bestiary I mentioned, this is already very non-trivial in the sense that we have order of thousands independent differential forms. And then we can also calculate topological invariants such as Euler characteristics to start to help fingerprint these geometries. However, I should admit very readily that these are all very coarse characterizations, meaning that they characterize totally generic Calabi-Yau hypersurfaces in weighted projective space, because I haven't used to get these numbers anything about the specific polynomial coefficients that arise in Feynman integrals. So in some sense, these Calabi-Yaus that I'm describing are the smooth varieties that appear when you desingularize the things that actually appear in Feynman integrals. And this is because it's much, much harder to characterize these singular geometries. But as such, a lot more work is needed to be done to characterize the actual manifolds. that Feynman integrals give rise to. So the types of questions this would help us address is whether or not any of the physics of the corresponding Feynman integrals are encoded in these geometries. It would be nice to be able to map out the phase diagrams of these integrals, meaning in which kinematic limits the manifolds simplify to product manifolds or become integrable in terms of polylogarithms. And it would also be nice to even be able to reliably determine when two manifolds of higher dimension are the same. In the elliptic case, we have the J invariant, and that tells us when two elliptic curves are isomorphic, but this becomes a much more non-trivial problem in higher dimensions. So with that, I will conclude. So I've mentioned that, or I've told you about the fact that geometric manifolds of arbitrary algebraic complexity appear in amplitudes, even in massless phi to the fourth theory and supersymmetric Yang-Mills theory. I've shown the rigidity or the dimension of the manifolds that appear in these integrals can be bounded at fixed loop orders. But at the same time, infinite classes of these integrals saturate these bounds and are therefore, in some sense, as complicated as they could be, and give rise to Calabi-Yau manifolds for reasons that we don't really know. And moreover, at two loops, we already encounter very complicated integrals that we currently can't evaluate in any way, shape, or form. So it's important to study these geometries at low loop orders so we can develop the technology to evaluate them in whatever form that would take. And I emphasize that a good understanding of these manifolds is still lacking, although Christian will, I think, have more to say about a specific class of integrals, the train track integrals that I haven't focused on in the next talk. So with that, let me thank you and remind you all that you should mark your calendars, and I hope to see you in Copenhagen next year.
Thank you very much, Andrew. Okay, time for some questions. I see there's one from Yorgos Papathanasio. You want to go ahead, Yorgos?
Hi there. Very nice talk, Andrew. I just wanted to ask, it's a clarification. So most of the things that you mentioned about also the particular classes or the definition of rigidity of boundedness was part of the first of the two papers that you mentioned in your beginning slide. Could you maybe elaborate what was the, if you presented, or what was the new content of the second paper, since it was also in your like beginning slide?
That had much more to do with these characterizations here, trying to understand better what manifolds actually appear in the Feynman integrals, also identifying these planar classes.
Mm-hmm.
Yeah.
So what was the main, let's say, conclusion of the second paper, or the as far as characterization or classification?
Yeah, so I mean, kind of what we want to do is just identify more precisely what types of manifolds actually show up in quantum field theory. Because right now, just saying that they're Calabi-Yau doesn't seem to tell us anything. For one, we don't know, even if let's say all Feynman integrals only give rise to manifolds that are Calabi-Yau, we don't know why that should matter. Certainly, we don't know, for instance, what it would mean for, you know, having Ricci flatness or something mean something in this context. So we want to identify more specifically if there's some physics that dictates the types of manifolds that show up, and to do that, one first wants to identify what they actually are. So we attempted to do so, and this is what we came up with, but I think this can be improved on quite a bit.
Okay, so for the time being, there haven't, it doesn't seem that there are any particular patterns appear as far as you said, some topological numbers of them or sorts, any kind of, they don't carve out, to your knowledge, a particular subspace.
Right, so most of the examples we know about, as I say here, can be realized as hypersurfaces in this type of way to projective space, which is a non-trivial statement. But part of the problem is we haven't been very good at characterizing the manifolds further. So we can't say much more about the manifolds that are singular. Although in the train track examples, I think we might be hearing more in the next slide that's a little more specific.
So not all Calabi-Yaus can be written as a cannot be embedded in weighted projective space. Only
this is a very special class.
I see. Okay, thanks.
I see a question from Enrico. Do you want to go ahead, Enrico?
Yeah, thanks, Lance. Thanks, Andrew, for this nice talk. So I have one question. So your analysis relies very much on the fact that you do this global Feynman parameterization in some sense, and then do your manipulations. But sticking with the examples that you have on exactly the slide that you have open, you know that, for example, you could try to do this two-loop integral here, this double box integral first in the wheel topology, to integrate that subtopology out in terms of a polylogarithm, right? You would get it as a weight 4 polylogarithm, and then you'd have to do one more loop integration over the remaining loop. So do you see anything like, could I violate your rigidity bound by doing something not in a global Feynman parameter way that you described, but in a more smart way by doing some sub-integrations first? The same applies actually to the train track. In the train track, I can integrate out the left loop and the right loop completely independently in terms of polylogarithms. And I'm left over one loop integral, the loop integral over the middle loop, times the product of these two polylogarithms. So do you see any interplay between your, what you claim these weighted projective geometries that you get from the Feynman parameterization to this more like tailored approach to certain topologies?
So I should have said that actually in these two specific cases, we did not do it by direct integration. We used a different method. So what we did is we started with a 2L-fold rational Feynman parameterization. And then just took as many residues as we could because it turned out to be too hard to do the direct integration. So this is not a surefire way of identifying kind of irreducible geometries. But since we're starting with a 2L-fold rational parameterization, we expect that basically every integration is transcendental. So in other words, for instance, in kinematic limits, you can check that you get the correct polylogarithm of weight 2L. In the limits that you can integrate in that way. So in that sense, we were able to identify every residue with kind of as mimicking a polylog integration. But there are some subtleties with that analysis that don't necessarily translate directly to the kind of functional forms that you might see if you were able to directly integrate into a space of functions.
So Yara tells me he has a question, so maybe we can turn to him now. Yara, do you want to unmute?
Yeah, just a quick question. So in the context of n equals 4 super Young Mills, so we know that two loops, this K3 shows up, but do you see that at the higher loops, you just kind of, everything shows up, you saturate the bound completely, or is there, can you say that some topologies actually don't show up in the end? In 5 to the 4, probably everything is just there, right? But
I don't have a concrete statement to make there. It would be very interesting to do a real taxonomy at 3 loops, for instance. As far as I know, this is the only this guy here is the only K3 at 2 loops, and we've identified Calabi-Yau 4-folds at 3 loops, but we've not done a complete taxonomy of what shows up and where.
okay, thanks.
Are there any other questions specifically for Andrew? Let's see, Nima. Go ahead, Nima.
Yeah, Andrew, I actually had a kind of a basic question. If we go backwards, if I hand you some candidate integral in parameter space, can you tell, is there like a fingerprint on it that lets you decide that you could have gotten it going backwards? I mean, so of course the denominators have to have the semantic polynomial, have to have the structure of the semantic polynomial. But is there anything or any constraints on the structure of the numerator that reflects, the fact that it comes from a Feynman integral? Can you get any numerator at all if you decorate, if you have arbitrarily complicated numerators in the integral to begin with? I'm just asking if there's some. For example, at one loop, I know that the dimensionality of the space is reflected in some, the sort of numerators that you get have some null spaces. It has to do with the gram determinants and so on. So there's some gram determinant downstairs in the quadrats you see downstairs, and the numerator has got to be annihilated by that null space if it actually comes from a 4-dimensional integral. Are there generalizations of that, or?
I haven't thought about it much. I mean, the semantic polynomial we start with is the scalar integral.
Right.
And I think it's fair to say that most of these graph theoretic ways of thinking about Feynman integrals
are just about the denominator. Yeah. Right.
Yeah, they don't know what to do with
Right.
numerators.
Right.
So, I mean, one thing that would be very interesting from my point of view would be to identify identities between these types of integrals. So, for instance, in the second paper on the first slide that Yorgos mentioned, we have a toy example where we can integrate in different ways, and we know we have to get the same geometry by symmetries, but the denominators look totally different, and we actually, it's not obvious to us that we would be able to see they were the same, but the dilogarithms in the numerator, I forget, might actually be different. So it could be that there are identities that know about both the denominators and the dialogues or whatever is in the numerator. And that would be very interesting. That's not quite the numerators you're talking about, but I would say we don't have a good understanding of the initial numerators either.
Thank you.
Thanks.
Hey, Matt had his hand up earlier, but maybe he's satisfied now to do it in chat. Matt, did you want to ask a question or comment?
Make the same comment I made in the chat, just in response to what Yara said, which is that we did look at diagrams with this sort of power counting and with the propagator counting Andrew described to sort of higher and higher loop orders, and high rigidity gets more and more common. So a larger and larger fraction of the diagrams seem to be maximally rigid and seem to have this embedding.
Thanks, Matt. Okay, at this point, I'd like to thank Andrew again, and then we'll sort of remain on the line for questions. I don't know if anybody's going to do a Slack channel. So thanks a lot, Andrew.
Thanks.